And here we are with another Java project. In this project, I used the Lejos NXT brick to build and design a parallel parking robot. This robot was built for my robotics class, which is a class I took for my computer science degree. Overall, this was a really fun class, which we focused on learning physics with robotics and how to implement different measurements into coding. The developers of this brick have multiple different resources to use when trying to build robots, such as the Differential Pilot class that I used, as well as the A-star algorithm class. Throughout the video, I'll give part of my presentation that I gave as a final in the class, which will go over the entire process of developing the procedure. Let's get right into it. First of all, the robot construction and hardware configuration. I originally had 3 builds to this. I added a caster wheel, which you can see in the picture to the left underneath the ultrasonic sensor. I used the Differential Pilot class as well in this build. The sensor is in a static position because I can turn this robot 360 degrees on axis to get a view around the vehicle. The ultrasonic sensor's role is to detect objects on its right side. If there's no object, then there must be a gap, and from there I can measure the gap distance, and if it's large enough, then I will be able to parallel park in the gap. So this is a software configuration as a high-level static view. First off, you start with the start thread, and I had 3 classes, which were the frame, run test, and page utilities. The page utilities pretty much just displayed the LCD screen, and the frame class, all it was just instantiating the run test file and starting that. And in the run test file, I pretty much had a couple functions. The first function is the run tests, which instantiates the button listeners, the differential pilot classes, the sensor, and instantiates the threads. Then in the run method, it pretty much just starts both of the threads to the right. So the 2 threads are the main thread. The whole point of the main thread is to process the robot's command. The display thread is to solely display the LCD screen. So here's just a little configuration of the 2 threads running. Once the threads are started and instantiated, it will go to the display thread on the right. It will display the LCD screen, then it will sleep for 250 milliseconds, and the main thread will be running. Then the only goal of the main thread is to process the robot command. Then it will sleep for only 10 milliseconds and continue running until the display thread gets called again. I'm gonna play a video right now of the robot actually working. So this was the extra credit video. It had to approach the objects at a 45-degree angle in order to get extra credit. There had to be 3 objects that were roughly the size of the robot, which I just used shoeboxes. And there had to be 2 gaps. The first gap has to be short enough that the robot can't park in, and the second gap has to be large enough for the robot to be parked in. The sticky notes are distances between the 2 parked cars. It cannot exceed greater than 1.5 times the robot's length. And finally, the robot has to emit a beep at the very end. So this is the software configuration of the process command of the main thread that we just saw. So currently I have 15 different states, and state 0 is the pose, and it creates the pose using the differential pilot. In state 1, it goes forward the size of the vehicle, and in state 2, it rotates 45 degrees. The first 3 states are for extra credit for my class project. After each completion of these boxes, it goes to the next stage unless specified otherwise by the arrows. If the boxes have multiple different outgoing arrows, then it has different states that it can go to, such as state 2 to state 3, or from state 2 to state 4. Right there, that is if I placed it at a 45-degree angle and trying to find the objects to the right. If there's no object, it will keep looping, but otherwise if there is an object, then it will move on to state 4. Similarly to state 7, if it calculates the gap size, if it's able to fit, then it will go to stage 8 and start the maneuver. Otherwise, it will move all the way back to stage 5 because the gap is too small. I also did some error checking when I'm aligning myself with the objects to the right. I get the distance with using the ultrasonic sensor, and then if I start drifting away to the left or right, getting closer or farther away, the sensor will detect that and then kind of align itself and angle itself away or towards, depending on if it was going closer or farther away, then it will try to go in a straight line. So here are all of the requirements for this final project. I was able to complete all of these requirements as well as the extra credit requirement. I'll go ahead and play another video for you. Then again, this is another extra credit video. As you can see, the robot is kind of jittering, and that is it deciding if it's actually getting closer or farther away from the object. This is the error detection that I was talking about previously. If it gets closer to the object, it kind of turns just a hair and then it keeps going forward, and if it starts going farther away, then it'll readjust again. This is real-time speed. The robot goes pretty fast, and its goal is to not touch the front or the back of the cars. The robot is able to be placed anywhere around 45 degrees and will be able to perform perfectly each time. Some of the challenges was using Legos. I sucked so bad at building. I had to rebuild 3 different times. The motors for the final build were not staying in place, and the wheel size measurements were a little bit different. These have to be absolutely precise, and I use a digital caliper to measure them, and it still seemed to be a little bit off. Multi-threading was a little bit difficult at first, but once I got a hang of it, I kind of understood it better. Using the Differential Pilot classes helped a lot because you could just say pilot.travel and it will move how your specified distance. All my measurements are in centimeters. And the disturbance was hard to get past as well. Like I stated earlier with the motors, the wheels were spreading apart as I was going straight, so it kind of veer off to the left or right, so I had to implement a feedback control system. And the caster wheel didn't really work well at all. The wheel did not spin whatsoever, so if I put it on carpet or something, it would most likely get stuck in the carpet, so I had to do it on a flat surface. What I thought was easy was the state machine. The Differential Pilot class was pretty self-explanatory. When I used the 15 different case statements, I could just step through them one by one, and I had to do specifically one task, so it was easy to write down using the Differential Pilot classes. And what I also thought was pretty easy as well was the feedback control system. So once I received data from the sensor, I put that data to use. So for example, the picture down below, the disturbance, let's say, could be the wheel spreading apart, so I would drift off to the left or drift closer to my objects and crash into them. But what I did was use that feedback, so the feedback was the ultrasonic sensor, and I was able to calculate the distance of how much I was moving closer or away from, and from there I would adjust accordingly. So the effort I put into this took me about 8 hours to build 3 different robots. It took me 9 hours to code the 3 different builds. Using the Differential Pilot class, again, helped me a lot because it had a lot of built-in functions that I would have had to program manually. And the documentation for this took around 6 hours. So I estimated 20 hours for work, and it ended up being about 23 hours, so not too bad. The documentation I thought took a little bit longer. I thought it wasn't going to take that long, and since I had to rebuild 3 times, it took me longer to build and code as well. I hope you all enjoyed this video. I like to document my journey receiving my computer science degree and hopefully prepare anyone who is interested as well. It was really interesting to see the different projects that other students came up with. Some of their projects included a cartographer, which maps out the surrounding area and displays it to a computer, a line follower, or even a calligraphy drawer. If you enjoyed, check out more projects like this on my website niha.com. Here, you can find unique videos that cover a wide variety of technology topics. You can also download the code to this project here. Don't forget to leave a like and subscribe. If you have any comments or questions, feel free to leave them in the comments below. Thanks for watching.